Hello YouTube viewers, welcome to my channel S2T. In today's show, Rocket Monday, we're gonna talk about Earth Observation Satellite. You may know them by other name like Remote Sensing Satellite. So let's dive right into it. Well, first you have to understand why the heck we do Earth observation. Well, we live here, so we can, we need to know. This is kind of priority data. This is more important than spying on each other. We need to know. Then the question becomes, okay, we are living on the ground. Why not use ground infrastructure to analyze this? The biggest limitation is that, well, Earth is not flat, unfortunately. So Earth is spherical. So what does that mean? That means no matter which kind of radar you use, which kind of Doppler system you use, they will always have an inherent limitation how far they can see. Now, when you want to study big weather patterns, including like tornado, cyclones, or things of that nature, they can travel hundreds of kilometers. So they will literally come out of nowhere in your radar system if you are utilizing ground based. So that has an inherent physical limitation. Basically, you cannot cover the whole planet, and not to mention most of the planet is covered by ocean. So even in land, let's say you did a lot of $1 billion investment to actually get those kind of coverage, on sea you will be useless. So that's the first problem. Then we have to understand this aspect. We need a global coverage. You cannot just like, okay, I'm analyzing like 100 kilometer of my border, and I'm gonna know which weather is gonna hit. No, that's not how it works. You have to know what's happening on the other end. Like heck, you need to analyze jet streams to figure out properly how the heck things gonna travel. So that is very critical. We need a global picture. Now, to understand the data that is coming in, the data must be up to date. It cannot be like, okay, I collected that data that is 5 hours, behind schedule. Yeah, that's useless. You need constant data. Basically, every minute you need this puppy to be refreshed as quickly as possible. And another aspect that is the biggest vulnerability of the ground-based system is that it is vulnerable. Like it goes down when you need it the most. So cyclone is happening, your radar system is most likely will be destroyed. Then you are talking about something that is analyzing snow. In blizzard it will get destroyed. That happens, always happens. So the time you need it the most, it will go down very quickly. But what about satellites? Like, I don't care. Like, you can have a sandstorm, satellites, I don't care. You can have a snowstorm, satellite still does not care. So that's the core reality. First, it removes the limitation of the fact that you cannot see only so far, but in space you can see almost all over the planet, especially if you are orbiting. And then you are 100% independent of ground-based events. And you might say, what about ground station? No company is going to build like one ground station. There are going to be multiple ground stations. So you will always have a working satellite infrastructure. Then, okay, that is the importance of satellite. Where do we place these satellites? Well, we place them in orbit, obviously, but you have to understand it. There are multiple types of orbit, from low Earth orbit to medium Earth orbit to geostationary orbit, and each orbit has their unique advantages. So you will never have like, okay, put it in this and forget about it. That does not happen. You will always have to fine tune what do you want to do, how to do it best. So generally, people start with low Earth orbit. Why? Because it's the cheapest. When I mean cheapest, as in like 1960s, we could not do better than that. And after a while, like lunar missions and all that, after a very long while, we actually started to put satellite in geostationary orbit. So that's the reality of it. Like, if you want maximum coverage, you need maximum number of satellite. Where can you get the maximum coverage for maximum number is low Earth orbit? Why? Because it orbits very quickly, so you're gonna get update every 20 minutes. And because it's cheap, your rocket is not so expensive. So you will be like, yeah, for the same price, I can have one satellite in geostationary, or I can have around 20-30 satellites in low Earth orbit. Every Tom, Dick and Harry is gonna pick 20 satellites. So that's the first point of usage. Then we come to SSO, Sun Synchronous Orbit, and this is kind of tricky orbit. Basically, it is a low Earth orbit, but it's a polar orbit. It's like a subcategory of polar orbit. So what people have done, that basically, if equator is like this, they're like, okay, let's make the satellite going like this. So it covers the polar orbits, north and south pole. Now it's tilted in a very unique way. Now that tilt is the amazing part. So you have to understand, Earth is spinning. Now your satellite is also spinning. So what does that mean? That means if the mathematics line up, you can create a scenario where you're gonna go, basically, let's say you crossing the equator, you're gonna cross equator every day, every orbit at 11 a.m. And like, wait a minute, isn't that only possible in geostationary? No. When I'm saying 11 p.m., I'm talking local time. Basically, whenever you are below the satellite, and satellite supposed to go ever 11, it will do 11. And they were like, okay, what happens if Earth move? That's the whole point. Whenever Earth will rotate, it will rotate in such a way that the next time the satellite crosses over, it's still 11 a.m. where the satellite is focused. Another place, same thing. So it's going above India, it's 11 a.m. If it's going above China, it's still 11 a.m. If it's going above Japan, still 11 a.m. because Earth is spinning. So that's the amazing aspect of it. So you will always get one time. So you can fine tune your orbit in such a way that, hey, at 11 p.m. I will get the most amazing photograph for, let's say, Google Earth. You're gonna put your satellite in that orbit, so you get exactly 11 a.m. So you are photographing India, 11 a.m. You are photographing Japan, 11 a.m. You are photographing America, 11 a.m. So that's why people want to use it so much. And if fine-tuned properly, you can have a scenario where a satellite's solar panel is always facing the sun. So that's the amazing aspect of it. That is why so much attention put into SSO, and that's why you were talking about like ISRO's a small satellite launch vehicle, Rocket Lab's Electron rocket, or the some third company that is just introduced the race. They are all talking about SSO, like we can put 300 kilogram to SSO. That's why, because SSO is amazing for orbiting, photographing the Earth and analyzing the same space again and again, specifically to time. So that's why SSO is very in very large demand. Then we come to the granddaddy, geostationary, because it's the furthest away. It has the basically the orbital rotational speed matches up the Earth's spin. So you're gonna be like absolutely still. Your relative velocity is zero. What does that mean, relative velocity? Both of you, basically Earth and satellite, they are traveling, but if you are standing on the satellite looking down to Earth will not look like spinning. But if you are on Earth, you're looking up to the satellite still not moving, so your relative motion is zero. The amazing part, that means you get 24 into 7 coverage of that exact place. It's not gonna show you like different place by how sun synchronous will do, like one orbit is gonna show you India, another orbit is gonna show you Pakistan, another orbit Iraq. That's not happening here. What you're gonna see is that what you're gonna get. However, you will get 24 into 7 coverage. There is no downtime or a blind spot. It's absolute. And another aspect is, because of the geometry and the sizes involved here, you can have as little as 3 satellites and get 100% Earth coverage. Basically, you can the amazing aspect of that would be, the only thing you will not know absolutely would be polar orbits, but you will be like, okay, this in equator, this tornado became big, this became cyclone big, and this is how it's traveling. You will get complete 100% coverage. That is why you will never hear any organization, be it ISRO, be it NASA, be it ESA, be like okay, we're gonna put our satellites here. All the satellites are generally spread around. You will never have like, okay, all the imaging satellites, they are in SSO. Sometimes imaging satellites will be in geostationary. Sometimes radar satellites would be in geostationary, but sometimes they will be in SSEO. So reality is, all of them work together to give you the perfect picture where you can be like absolutely damn sure. Because I'm reasonably sure any of you are in like around reaching your 30s, the fact that in older days when you are a kid, the news was like a tornado is gonna hit, evacuate this whole area. Now it's like tornado is gonna hit this county. It's like, okay, this exact location tornado is gonna hit, and it hits it. Like nowadays it's a running gag in our family. It's simply because if a newspaper says it's gonna rain, it rains. Like we cancelled Holi celebration based on that, and yeah, it rained on that day. It's that precise. Why? Because we have so many points of view, and all of them are giving us 100% perfect coverage. Now, there are many tools that are used, like that's where we put the satellite. Okay, what types of satellite? So primary satellite, how we began this whole journey is from optical satellite. Now optical satellite gives you multiple spectrum to study. That simply means we are generally talking about red, blue, green, RGB, and sometimes infrared also. Now visible spectrum is key simply because it's the easiest to understand. I show you a photograph of tornado, you know what it is, you know how it's moving, and if the photograph is high resolution enough, you can even figure out things like, hey, what is the average water droplet size? Hey, what is the average temperature? Because again, different temperature, different brightness would be there. So many things can be gleaned to. If you have a high resolution photograph of a tornado, you're like, I got this. This is what's happening. This is how the weather is gonna move. That's priceless. And then we come to the infrared. Now infrared is kind of very important simply because everything in weather relates to temperature. So understanding temperature is very crucial. And temperature, the tricky part is that it's not infrared. When we say infrared, people assume infrared. In reality, infrared is a band, and this band is actually bigger, fatter than what we call visible spectrum. So side effect of that means is like, sun is pumping energy into earth using infrared, but it's doing it in different spectrum. Now earth is radiating that heat away in different spectrum, so you have to study two different spectrum, and they are literally far apart in electromagnetic spectrum. So to understand this kind of photograph, you have to have very complicated infrared measurement unit, where you can be like, okay, on the day side when I'm observing the daytime, I'm observing how sun is putting energy in. On night side, I'm gonna study how earth is radiating that heat away. Combine those data, then you're gonna get amazing pictures like this, where you go like, okay, tornado is gonna form here and it's gonna travel this way. Why? Because that's the thermal pathway allowed for it. So that's the amazing reality of it. This, if we combine both of the data, optical spectrum data and basically thermal infrathermal rates radiation, we get absolute control pictures. Like this is what, and this is how it's happening. Then how the heck we focus it, basically which area. These orbits are generally in low earth orbit, sun synchronous orbit, so how much area do we cover? That depends on the science mission. So if this mission is like, yeah, it's a science mission but we want to spy a little bit, so they will generally not use wide coverage, because wide coverage gives you the biggest picture but it reduces your resolution. So per pixel resolution would be like, 1 pixel represents 30 square meter. Benefit, you're gonna get 100% coverage of the earth, but your resolution would be very low. It's very good for weather system, not good for spying. But if you want to do spying system, or you want to study like foliage, basically how land masses are reacting, how cities are growing, of that nature, where you need precise data, you're going to use for a telephoto lens. Telephoto lens side effect, it will not give you coverage, because you have to wait for like, it to properly go around the earth again and again and again, and then you're going to get a complete picture. But is going to give you high resolution data. So mathematically, the highest people have successfully achieved is so high is that you walk out of your home, the satellite can see that in low Earth orbit. Now your clothes color, and if it's a car, AI can fine tune is like, okay, this car, this model, and all that jazz. Yeah, license plate, no, that's not happening, but it can come very damn close. It's like very damn close we can reach that. And the reason we cannot go any further is not because we cannot put bigger satellites there. The side effect is like Earth atmosphere is always shimmering, so because of that you cannot tangibly observe any further than that. So you are talking about like, per pixel around half meter. So these are optical satellites. These were the first thing we put into place, and this is the like, backbone of our weather system. Then we come to the radar satellites. Now earlier, in early days, we simply did not use solar panels, were not a big thing, and like Soviet Union actually put nuclear reactors to make a radar system. Now benefit of radar system, it's simply not affected by weather. You have sandstorm, it does not care. You have tornado, it does not care. You have a snowstorm, it simply does not care. It works 24/7. So let's say you are like in a place like Canada and you have to analyze your road infrastructure. Half of the time, again, it's night, so you cannot observe it. Another half of the time, let's say when it's day, probably most of the place is covered in snow or fog or things of that nature, so flat out useless. Radar, it does not care. It can give you photos like this. Now, and these are black and white image. Again, it's converted for human eyes, so you can easily understand it. But this is quite amazing, feat, because it removes atmosphere. It flat out removes atmosphere, and on top of that, radars are very specifically tunable. You like in your camera, you cannot do too much tuning in terms of red, blue, green. You cannot do much. But in radar, because it's a positive active system, basically it sends out the ping and then waits for its receival. You can fine tune it. It's like, hey, send spectrum in. Basically how your Wi-Fi router does that. Like your Wi-Fi router is technically 2.5 gigahertz, but somehow it can talk to 5-6 mobile phones, because it's fine tuning. It's like, okay, for that mobile phone I'm gonna say 2.56, 2.52, 2.59. It's doing that. It's creating sub channels into that. Radar is an active system. Now when you're sending system, some people have figured out, hey, what if we send different band, K band, KU band, or this thing or that thing? Benefit are each of them react differently to different architecture. So you can have that. This can give you data like how good is the health of your fish. Like, what the hell? That's simply because specific radar will react specifically to the masses of fish. So fine tune that, you can easily sense that. So that's the amazing part of it. That's why people spend so much in radar satellite. Like if you are in Dubai, you want to have radar satellite as your infrastructure analysis, simply because sandstorms, it can see through it. So that's why people spend so much, like ESA spends so much money into radar systems. Now we have to, so far both of things I talked about, generally they are one-click system. You take a photo, you send it for ground team to analysis. Now those two photographs that we are talking about, those are generally two-dimensional photograph. Then we introduce the third dimension photography, which is called multi and hyperspectral imaging. Now what you have to understand here is that electromagnetic spectrum is huge. It's huge. Like if you want to specify that how huge it is, like you take the spectrum, you stretch it to kilometer, you'll barely get few meters in visible spectrum. So it's we see a very tiny sliver of that. Now we can make instruments that can see infrared. We can make instrument that can see specific bands in infrared, because infrared is huge. It's like, it's kind of fat band. So we have near infrared, mid infrared, far infrared, like these three bands. And what if you made multiple slices in that? So that creates the reality of what we call multi and hyperspectral imaging. So you will always see photographs of sun where sometimes sun is like blue, sometimes it's green, sometimes it's like all that. All they are doing is showing you the truth, but truth is in like different color. We cannot see it. So computer generally change the color code. So benefit of that is hyper spectrum photography is basically because of that spectrum you can study so many things that you would thought impossible. Basically, if you think why people ESA is saying, hey, we're gonna build this satellite and it's gonna help our agriculture, you're like, what the hell is gonna do with agriculture? It can tell you the nitrogen component of the soil. Like, how? That's how it's doing that. Because if you want to study nitrogen is going to behave to electromagnetic spectrum differently. So that's the reality of it. Different part of wavelengths tells different story. So you can take a photo, all you are seeing are red, blue, green. But if you take photograph in infrared and not in like narrow band infrared, like multiple bands infrared or hyper band infrared, you're going to be like, in this band, if this is bright, that means it has nitrogen, and we utilize that. That's the reality of it. Like when you see this high color contrast images, generally they are hyperspectral. Benefit of that, you can study through things. Like the photograph you take generally has depth to it. It's not okay, it's not just red, blue, green. It has a depth to it. In each depth you will have different slices. You will have one slice of ultraviolet, another slice of infrared, another slice of high infrared, another slice of soft infrared. Analyzing all of these slices, so to say, the multiple slices that you are taking on, that gives you so much data that you can literally study the health of a forest. You can tell, hey, I think somebody is contaminating the groundwater of the forest because the nitrogen component is going that low, or the albedo of forest has changed. So because again, in one RGB you can see some things, but when you're talking about hyper, you can see everything. It can tell you the quality of the soil. It can tell you the water bodies. Basically, you can tell, hey, the algae blooming is happening here before people can see it, like because the spectrum will change. Again, it's not visible to human eye, but to a hyperspectrum system it can be easily seen. So that is why it allows us to see a complete photograph. Whenever you see people talking about, hey, it's gonna do ozone observation, that's how it's doing that. It's not gonna see like, okay, one thing done. Again, it will have like, hey, ozone reacts to this spectrum very well, so they're gonna take that spectrum, 2-3 spectrums, plus and minus, to get complete picture of that. And for agriculture, this has been a godsend, because like state by state you can know, hey, this state is dealing way too much with nitrogen, because the water that they are getting is contaminated, and it already has too much fertilizer in it, and that's why their crops are dying. Like on a state level you can do this kind of analysis. You can like literally see, and if the focus beam, like specifically if you have wide and telelens, if you use telelens, you can tell, hey, these people are doing this kind of bad things. It is quite amazing what can be done with this hyperspectrum and multi. And if you want to understand the difference between that, multi simply means you will have few fat slices. Hyperspectrum means you can have very fine tuned. It's like one is high megapixel, another is small megapixel, in the Z direction, not in XY, in the Z direction. So these are the three major tools that we use for remote sensing, aka observing something from the far away. So this was my presentation on remote sensing satellite or Earth weather satellites. I hope you liked it, learned from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I'd urge you to press dislike, press it twice to show me your disappointment, and please leave a comment because I try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.